Okay. Hi guys, so my name is Judy and I'm going to be showing you how to do an AP Physics C problem. Okay, so this problem, again, you have 15 minutes to do them. There are about 4 parts and it's worth 15 points, and it's important to show work in everything that you do. Okay, so the question reads, a 100-kilogram box shown above is being pulled along the x-axis by a student. The box slides across a rough surface and its position x varies with time t according to the equation x equals 0.5 t cubed plus 2t, where x is in meters and t is in seconds. So the first part asks to determine the speed of the box at time t equals 0. They give you the equation of what x equals. So we know that velocity equals dx dt. So now from here, we can find the velocity by finding the derivative of x. So x, we said, equals, the equation tells us 0.5 t cubed plus 2t. So the derivative of this, which would equal dx dt, would equal, you would have to multiply the exponent times coefficient, so 3 times 0.5, bring down the variable, take 1 off from the exponent, so 2, and same thing again with the 2t. So you have 2, and then the exponent here is 1, so 1 subtract from that is 0. Now simplifying, you get 1.5 t squared plus 2. Now they want to know, this is velocity. Now they want to know the speed at time t equals 0. So for that, all we have to do is simply plug in. So velocity at 0 equals 1.5 times 0 seconds plus 2. Again, simplifying this, we get 0 and then a 2. So velocity equals 2 meters per second. Okay, now part B says, determine the following as functions of time t. Part BI says the kinetic energy of the box. So we need to find, well, the kinetic energy of the box. We know kinetic energy equals 1/2 mv squared. Now, we know what the mass is, and we have just found out what the velocity is. So we can simply just plug in. So kinetic energy equals 1/2 times the mass, which is 100.00 kilogram, times the velocity squared. Over here, we found the derivative of velocity. Oops, you can't see it. Over here, 1.5 t squared plus 2. So now if they wanted to know the kinetic energy as a function of time, we can just plug that in. So we have velocity as 1.5 t squared plus 2, and all of that is squared. Simplifying this, we can multiply the 1/2 and the 100, so we get 50.00 kilogram times 1.5 t squared plus 2 squared. And that is the kinetic energy. Now part 2 of B asks the net force acting on the box. So for net force, we know that force equals ma from Newton's second law. So we write F equals ma. We know what the mass is, but we don't know acceleration. But we can find acceleration by finding the derivative of the velocity. So if velocity equals 1.5 t squared plus 2, find acceleration. So we know that acceleration equals dv dt. So the derivative would be, again, multiply the exponent by the coefficient, so 2 times 1.5, and then subtract 1 from the exponent, so just t, because 2 minus 1 is obviously 1. And now constants, the derivative of a constant is always 0, so just put the 0. Now we can simplify and write that as 3t, and this is acceleration. So now, when the question asks us for the net force, all we have to do is plug in. Force equals ma. our mass is 100.00 kilogram, and our acceleration is 3t. So we get 300 t. Alright? I think I'm going to change to a different piece of paper now. Hold on. Okay. So the next part in the question asks us for the power being delivered to the box. Well, we know that power equals work over time. Now, work can be represented by force times the displacement over time. Now, you can see that x over t is velocity, so power breaks down to force times velocity. Now, using all of the equations that we've already previously discovered, we can plug in and simply find the power. So power equals force times velocity, which equals 300t times 1.5 t squared plus 2. Again, we can simplify this to 450 t cubed plus 600 t. Again, the two equations listed here were discovered in the previous steps of the question. So that is our power. Now, part C asks for the net work done on the box in the interval t equals 0 to t equals 2 seconds. So we know that work equals the change in kinetic energy. So it's the change in kinetic energy is simply the kinetic energy final minus kinetic energy initial. That breaks down to 1/2 mv final squared minus 1/2 mv initial squared. So since the mass is the same, we can make this equation simpler and bring out the 1/2 and the m. So we have 1/2 m times velocity final squared minus velocity initial squared. Well, we know what the velocity initial at 0 seconds was from part A, but we need to find what the velocity is at 2 seconds. So we can do that by substituting in the variables to what we had as the previous question. So velocity equals 1.5 t squared plus 2. But we're looking for velocity final vectors, which this is at 2 seconds. So 1.5 times 2.00 seconds squared plus 2. This all breaks down to 8.0 meters per second. This again is our V final. Okay. So now that we know what the velocity final is, we can plug into our equation over here and find the net work being done. So again, work equals 1/2 m times V final squared minus V initial squared. So the mass is 100 kilograms. V final is 8, so 8.0, we'll add another sig fig, meters per second squared, minus the velocity initial at 0, which we found in part A, to be 2 meters per second, so 2.00 meters per second squared. Now this all, when you calculate it out, will equal 3,000. And since we're finding work, the correct unit is joules. But if we look at our sig figs, we should have 3 significant figures. So we can write it as 3.00 times 10 to the 3 joules. And this is our answer. Alrighty. Now, the last part, let me bring it back here, asks for it says, indicate below whether the work done on the box by the student in the interval t equals 0 to t equals 2 seconds would be greater than, less than, or equal to the answer in part C. Okay, so this basically is a check answer, and what the answer would be is greater than. The reason for that being, they want to know the work done on the box by the student. The student has to overcome a frictional force. So when the work the student performs involves, let me see if you can see what I'm writing. So the work of the student would equal, again, the change in kinetic energy, but it would also have to incorporate the work of the friction force. With this, we can easily see that the work done by the student will be a lot greater than what we had in C, which was just simply kinetic energy. And that is the end of the question. So basically, this question involved manipulation of the original equation, finding derivatives, and then plugging in with your formulas. It wasn't too bad, and it can be done. So hopefully this helped all of you, and yeah, that's it for now. Thank you. Bye.